The National Electrical Code, or NEC, does not permit the use of metal sheathing on electrical cables such as BX, MC, or AC as the sole means of equipment grounding. Utilizing the metal sheathing alone poses a potential safety hazard if the sheathing becomes damaged or inadvertently disconnected. To ensure electrical safety and code compliance, a separate equipment grounding conductor is mandatory. This conductor provides a reliable, low-impedance path for fault currents, facilitating the quick operation of overcurrent protective devices like circuit breakers or fuses in the event of a ground fault. The equipment grounding conductor can be either a bare or insulated wire. When using an insulated equipment grounding conductor, it must be visually identifiable, typically by being green in color or green with one or more yellow stripes. This distinct color coding helps electricians easily identify the grounding conductor during installation and maintenance. The equipment grounding conductor must be connected to the equipment grounding terminal on the receptacle. This terminal is usually a green-colored screw or a pressure connector specifically designed for grounding purposes. The connection must be secure and made in a manner that ensures good electrical contact. Furthermore, the equipment grounding conductor must be connected to the grounding system of the building. This grounding system typically consists of a grounding electrode system, such as a ground rod, ground ring, or metal and a groundwater pipe that is in direct contact with the earth for at least 10 feet. A connection between the equipment grounding conductor and the building's grounding system ensures that any fault current will have a direct path back to the source, allowing overcurrent protective devices to trip and energize the circuit. Consider a scenario where a fault occurs within an appliance connected to a receptacle wired using BX cable with only the metal sheathing serving as the equipment ground. If the metal sheathing has become compromised due to corrosion, physical damage, or a loose connection, the fault current may not have a low impedance path back to the source. This can result in a dangerous voltage potential on the appliance's metal parts, posing a shock hazard to anyone who comes into contact with it. Additionally, the limited fault current may not be sufficient to trip the circuit breaker, allowing a fault to persist and potentially cause a fire. In contrast, if the receptacle is wired with a separate equipment grounding conductor connected to both the receptacle's grounding terminal and the building's grounding system, the fault current will have a clear and reliable path. This will cause the circuit breaker to trip quickly, de-energizing the circuit and eliminating the shock and fire hazards. The NEC specifies requirements for the size of the equipment grounding conductor based on the rating of the overcurrent protective device protecting the circuit. Table 250.122 in the NEC provides guidance on the minimum size of equipment grounding conductors for various circuit ratings. It is crucial to consult this table and select the appropriate size conductor to ensure adequate fault current carrying capacity. In older homes where BX cable without an equipment grounding conductor is present, there are several options for upgrading the grounding system to meet current code requirements. Firstly, the existing BX cable can be replaced with a cable that includes an equipment grounding conductor, such as MC cable or NM cable with ground. This is the most comprehensive solution as it ensures that all new wiring meets current safety standards. Secondly, a separate equipment grounding conductor can be installed alongside the existing BX cable. This conductor can be run from the receptacle back to the main grounding system of the building, providing a dedicated ground path. Thirdly, a ground fault circuit interrupter, or GFCI, receptacle can be installed. GFCI receptacles are designed to detect even small amounts of current leakage to ground and will trip quickly, de-energizing the circuit and preventing electric shock. While GFCI protection does not provide a true equipment ground, it offers a significant improvement in safety compared to relying solely on the metal sheathing of BX cable. It is important to note that using a GFCI receptacle does not eliminate the need for an equipment grounding conductor in all situations. The NEC specifies certain conditions under which GFCI protection is permitted as a substitute for equipment grounding, but it is crucial to carefully review the applicable code sections to ensure compliance. When working with electrical systems, it is always best to consult with a qualified electrician to ensure that all work is performed safely and in accordance with the NEC. Electricians have the knowledge, skills, and experience to properly assess the existing wiring, identify potential hazards, and recommend appropriate solutions to ensure the safety of the electrical system. Furthermore, it is imperative to remember that electrical work can be dangerous, and it should only be performed by qualified individuals. Working with electricity without proper training and precautions can lead to serious injury or even death. Therefore, it is always best to leave electrical work to the professionals. In summary, the NEC prohibits the use of metal sheathing on electrical cables as the sole means of equipment grounding. A separate equipment grounding conductor is required to provide a reliable and safe path for fault currents. This conductor must be properly connected to the receptacle's grounding terminal and the building's grounding system. When upgrading older wiring systems, consider replacing the existing cable with one that includes an equipment grounding conductor, installing a separate grounding conductor, or using GFCI protection in accordance with the NEC. Always consult with a qualified electrician to ensure that all electrical work is performed safely and in compliance with the applicable codes and standards. To further clarify, consider the specific requirements outlined in the NEC regarding equipment grounding. Article 250 of the NEC covers grounding and bonding requirements in detail. Section 250.4 addresses general requirements for grounding and bonding, emphasizing the need for a permanent and continuous electrical path to ground. Section 250.118 lists acceptable types of equipment grounding conductors, which include copper, aluminum, and other conductive materials that meet specific requirements for conductivity and corrosion resistance. Metal cable systems like NEC cable are permitted to be used as equipment grounding conductors if they meet certain conditions outlined in the NEC. These conditions typically include requirements for the type of metal used, the thickness of the metal, and the presence of a supplemental grounding conductor within the cable. However, BX cable, which typically lacks a separate grounding conductor, is generally not permitted to be used as the sole means of equipment grounding. Section 250.130 addresses methods for grounding existing branch circuit extensions. This section allows for certain exceptions to the general grounding requirements when extending existing circuits that do not have an equipment grounding conductor. These exceptions typically involve the use of GFCI protection or the installation of a grounding conductor from the extension back to the main grounding system. However, these exceptions are subject to specific limitations and conditions, and it is crucial to carefully review the applicable code sections before implementing them. It is also important to consider the impact of voltage drop on the performance of the equipment grounding conductor. Voltage drop occurs when current flows through a conductor, causing a reduction in voltage at the load end. Excessive voltage drop can reduce the effectiveness of the equipment grounding conductor, potentially delaying the operation of overcurrent protective devices during a fault. The NEC provides guidance on calculating voltage drop and specifies limits on a maximum allowable voltage drop in branch circuits and feeders. When sizing equipment grounding conductors, it is important to consider the potential for voltage drop and select a conductor size that will minimize voltage drop and ensure adequate fault current carrying capacity. In addition to the NEC, other standards and regulations may also apply to equipment grounding. These may include local building codes, industry standards such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and product safety standards such as those published by Underwriters Laboratories, or AL. It is crucial to be aware of and comply with all applicable standards and regulations when designing, installing, and maintaining electrical systems. Proper equipment grounding is essential for electrical safety and is a fundamental requirement of the NEC. By following the code requirements and best practices for equipment grounding, you can help protect people and property from the hazards of electrical shock and fire. Always consult with a qualified electrician to ensure that all electrical work is performed safely and in compliance with the applicable codes and standards. Furthermore, consider the specific applications and environments in which the electrical system will be used. In some cases, additional grounding measures may be necessary to address specific hazards or requirements. For example, in healthcare facilities, additional grounding and bonding requirements are often specified to minimize the risk of electrical shock to patients and staff. Similarly, In industrial environments, additional grounding measures may be necessary to protect sensitive electronic equipment from damage due to electrical noise or surges. When designing and installing electrical systems in these types of environments, it is crucial to carefully consider the specific requirements and implement appropriate grounding measures to ensure safety and reliability. Consider surge protection devices, or SPD, which are designed to protect electrical equipment from voltage surges caused by lightning strikes or other transient events. SPD are typically connected to the electrical system at the service entrance or at individual equipment locations. To be effective, SPD must be properly grounded. The grounding conductor for an SPD should be as short and direct as possible to minimize impedance and ensure that the surge current is effectively diverted to ground. Improper grounding of SPD can reduce their effectiveness and may even damage the equipment they are intended to protect. Furthermore, consider the use of equipotential bonding. Equipotential bonding involves connecting all metal parts that are likely to become energized during a fault to a common grounding point. This helps to minimize voltage differences between these parts, reducing the risk of electrical shock. Equipotential bonding is commonly used in swimming pools, spas, and other areas where people may come into contact with water and electrical equipment. When implementing equipotential bonding, it is important to use appropriate bonding connectors and conductors and to ensure that all connections are secure and reliable. In addition, consider the importance of regular inspection and maintenance of the grounding system. Grounding connections can become loose or corroded over time, reducing their effectiveness. Regular inspection and maintenance can help to identify and correct these problems before they become a safety hazard. During inspections, check for loose connections, corrosion, and damage to grounding conductors and connectors. Repair or replace any damaged or corroded components as needed. Also, test the grounding system periodically to ensure that it is functioning properly. Grounding system testing typically involves measuring the impedance of the grounding path to ensure that it is within acceptable limits. If the impedance is too high, it may indicate a problem with the grounding system that needs to be addressed. Remember that proper equipment grounding is not just a matter of complying with the NEC or other regulations. It is a fundamental aspect of electrical safety that can help to protect people and property from the hazards of electrical shock and fire. By understanding the principles of equipment grounding and following the applicable codes and standards, you can help to ensure that electrical systems are safe and reliable. Always consult with a qualified electrician for any electrical work and never attempt to perform electrical work if you are not properly trained and qualified. Finally, remember that technology and best practices in electrical safety are constantly evolving. Stay up to date on the latest developments in the field and continue to learn and improve your knowledge and skills. By staying informed and committed to safety, you can help to create a safer environment for yourself, your family, and your community. The information provided here is intended for general educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or other professional for specific guidance on electrical safety and code compliance.